Hello everyone and welcome to this tutorial. My name is Peguy Kem-Meka, and in this video, I'm going to talk about the shape of data. But before that, let's try to solve this small problem. Imagine that I perform an experiment and collect my data, and they are depicted in this figure. I would like to know the relationship between the feature. We can see that when X increases, Y increases as well. So there is a strong linear correlation between my variables. Linear regression in this case allow me to get this line of best fit, which is the shape of my data. This line can help me, for example, to do some prediction, or more generally, to build predictive model. What if my data are no more linear? For example, this one on this figure. You can see that linear regression can no more be effective for this kind of data. And it is even harder when I am in high dimensional, let's say dimension greater than 4. Therefore, we need a method that helps us to discover the shape of my data. This is when topological data analysis come into play. Topological data analysis uses the notion of homology to deduce the shape of the given data. Homology is just an algebraic object that assigns to data a certain number called signature or Betti number, and that gives me an information about the shape. For example, if my data is just a point, the Betti number 0 will be 1, the Betti number 1 will be 0, the Betti number 2 will be 0, the Betti number 3 will be 0, and all the rest of Betti number will also be zeros. If my data is instead a torus, my Betti number 0 will be 1, my Betti number 1 will be 2, my Betti number 2 will be 1, and all the rest of Betti number from 3 will be 0. So when I have my data, I can always compute Betti numbers to detect the shape of my data. But there's a problem. Real-world data do not always come with very nice shapes and smooth, well-formed shape like this one for us to compute the homology and detect the shape. Real-world data usually come as a point cloud in some Euclidean space, and it is then our task to build object on top of it, and these objects are called simplicial complexes. To define the notion of simplicial complex, we need first to know the one of simplicity. A n-simplex is just a convex whole of n plus 1 affinely independent point. In other words, here I have my point v0, v1 up to vn. Satisfying this formula star, I will say that they form a n-simplex. For example, a 0 simplex is just a point. A 1 simplex is just an edge. A 2 simplex is just a triangle. A 3 simplex is a tetrahedron. Then now define the notion of simplicial complex. A simplicial complex is just a finite collection of simplices satisfying A and B. For example, on the left-hand side here, I have a valid simplicial complex. On the contrary, on the right-hand side, I have here a invalid simplicial complex, because you can see here that the intersection of these two simplexes are no more a simplex in both. Since I know already the notion of simplicial complex, let's give this workflow. We will always start with data which are point cloud. We will have to build simplicial complex on top of it, which correspond to graph, therefore a geometric object. Having the simplicial complex, I can compute the so-called chain complex, which is a vector space associated to the n simplices. Having the vectors, having the chain complex, which is the vector space, I can compute the homology group, which is also an algebraic object, and which is defined as a quotient vector space. This is my sim Astra. Let's consider this working example. I always start with my data here, 5 data points. I have to build graph on top of it, which are simplicial complex. Here is simplicial complex X. Having my simplicial complex, I can start defining the notion of a chain complex Cn of X, which correspond to the n simplices, n in 0, 1, 2, up to some natural numbers. For example, when I want to compute the C0 of S, I'm computing the vector space with basis the 0 simplices. The 0 simplices are V, W, X, Y, Z. I can also compute C2 of X, which is a vector space with the basis the 2 simplices. Here I have only 1, 2 simplex K. That's why C2 of X is Z K. Z2 of K. Z. Since I don't have any high dimensional simplices when n is greater or equal for Cn of X will be 0 when n is greater or equal 3. Let me point out that here we are working with the field of coefficient Z2 because it's more practical when we are doing topological data analysis. Having the simplicial complex, I can now compute the n homology, which correspond to the n cycle divided by the n boundaries. For example, the 1 homology is a 1 cycles divided by the 1 boundaries. Cycles here are in the sense of graph theory. So the 1 cycles here are A plus B plus C. That's why I have this. And D plus E plus F. That's why I have this second cycle. Now, when I divide by 1 boundaries, I have only here a boundary of a 2 simplex. That means the boundary of K. The boundary of K is just this A plus B plus C. Simplifying my relations, I will have D plus E plus F as the base of the first homology group. We are explaining that there is a hole here on my simplicial complex. Therefore, we can see that the first homology is just giving me the shape of my simplicial complex, since the Betti number 1 is 1. Hence, the simplicial complex X has a 1-dimensional hole. Now that we know already the notion of simplicial complex and homology, this is the workflow or the pipeline for you to know the shape of your data. I always start with data, which I point in some Euclidean space. I compute an algebraic object on top of it. From the algebraic object, I can compute the homology that will help me to know the shape of my data. For example, we computed the first homology here, and we have seen that there were a hole here. Having now the shape of data, I can do some statistical analysis, or I can fit it. I can fit some machine learning algorithm with it to do some artificial intelligence task. In this pipeline, the more difficult part is moving from data to algebraic object. But there are several algorithms like check complex, Victorius-Rips complex, alpha complex, Witten complex, cubical complex. But here I will limit myself on the explanation of the check complex. We always start with data here corresponding to 1, 2, 3, 4, 5, 6, 7 data points. We build poles around each point with a certain radius R. When 2 balls intersect, we build a 1 simplex or an edge. When three balls intersect, we build a two-simplex. More generally, when k plus 1 balls intersect, we build a k-simplex. This is nice, but you might ask yourself, how do we choose R? In fact, we don't choose any value of radio. We consider all possible value of radia, and we keep track of the evolution of the homology associated to each simplicial complex for a given radius. That means that this pipeline was not totally correct. Let us rectify it. I start with my data, and as I am building ball around each point with a certain value of radio, I will get many algebraic objects. Therefore, data, the pipeline is data and then algebraic or sequence, family or sequence of algebraic objects. And for a given algebraic object, I will have to compute the homology, which give me the shape of my data. And I will just consider the shape that persists the most as the radio R is evolving. This is an introduction of the notion of persistent homology. Thank you for watching this video, and bye-bye.